Hey everybody, I'm Gabe. Welcome to my presentation. I'm going to be talking about the UH-60 Blackhawk's primary flight control system. So, to start off with a general overview of what I'm going to be talking about today is a basic introduction to helicopter flight, the Blackhawk's flight control system and the components that make up that system, the normal operating conditions of the system malfunctions, and then alternate operating conditions that the pilots will have to fly the system with if it does malfunction. So, for a general introduction, for those of you who are not acquainted with the Black Hawk helicopter, it's a medium utility helicopter that entered service with the U.S. military in 1978. It's a versatile helicopter that can fulfill a lot of different roles, such as troop and equipment transport, medical evacuation, search and rescue roles. You can do a whole lot of things with the helicopter. You can have soldiers parachute out of it or slide down ropes out of it. You can carry artillery underneath it. You can put missiles on or machine guns on it. It can do a whole bunch of stuff, which is what makes it so great. It's typically got a crew of three, two pilots and one crew chief. And just a note, the technical document that I used for this presentation, it was going off of the UH-60Q model. So that's the specific model for the information that I got. And now normal operating conditions. In general, for most helicopters, flight controls consist of a collective pitch control lever, a cyclic stick, and tail rotor pedals. So you can see in the picture in the bottom left here, item number one is the foot pedals. They look just like normal airplane rudder pedals. Number two is the cyclic pitch lever. That looks like a stereotypical fighter jet's control stick. It goes between the pilot's legs. And then number three on the side of the pilot's seats, unique, doesn't really look like anything except for a helicopter collective is the helicopter collective. It looks like a long handbrake in the cockpit. So control inputs made by the pilots are transferred from those controls to the rotor blades via mechanical linkages and hydraulic servos. The servos are there to, the way I see it, kind of multiply the pilot's physical forces on the controls. That way it achieves a greater amount of controlled surface deflection, so it makes the pilot not have to work as hard. We'll get into that later. But they do have dual cockpit controls, including the Black Hawk, so two sets of separate controls, but there is a mixing unit within the helicopter that will combine, sum, and couple the control inputs from both sets of the controls, so that way the pilots can help each other on the controls and things like that. Next up, we have the main rotor assembly. So this obviously sits on top of the helicopter fuselage, and it is connected to the fuselage by the rotor mast, which is the big, just a pole in between the rotors. Other major components include the swash plates. So we have a lower swash plate, which is fixed in place, and then a row of ball bearings between that and the upper swash plate. And the upper swash plate is free to rotate and spin, unlike the lower swash plate. And these rotor blades that are connected to the swash plates are airfoils, just like typical wings. So they create lift because they split air coming over them. So some air goes over the top, has relatively higher speed, lower pressure, while the air below them has relatively lower speed but higher pressure, and we all know that's what creates lift. And in between these major components are then control rods that are part of the transferring process of the pilot's controls to the rotor blades themselves. And also in the picture you can see the Jesus nut labeled on top of the rotor mast, aptly named because if it fails, the rotor fails and the crew gets to meet Jesus, as they say. Next up is the collective pitch control stick specifically. So you can see it in the picture there. It's again that long handbrake looking device, and it's got a weird grip on top of it. So that's the helicopter's throttle control. I'll talk about that in a second, but that's where it's located, right on the tip of the rest of the collective pitch control stick. But the stick itself controls vertical movement of the helicopter, so that's straight up and straight down, something that pretty much only a helicopter can do. And it does this by varying the pitch of the main rotor blades, causing an increase or decrease in lift produced by the entire main rotor disc. The term main rotor disc is just basically the circle that is created by the rotors as they spin. So whatever control input the pilots make on the collective, that input is going to take effect uniformly across the board, across all of the rotor blades. You're going to have the same synchronized effect. It's all going to affect them the same. So for example, when the pilot lifts the collective upwards, that movement is transferred, again, via mechanical linkage and the hydraulic servos to the swash plates, to the control rods, which then manipulates the rotor blades themselves. In this case of an upward input, the blades would increase in pitch and create more lift. So on this next page here, this will talk about, oh yes, the throttle on the tip of the collective. So twisting that grip is going to change the propeller blade's RPM, and it also has a friction control function to prevent the stick from creeping, just like the throttle friction lock in the Cessna 172 that we're all familiar with. So it does the same concept, same thing. And also on the stick grip are a variety, a whole bunch of different controls. You can see I have them listed here with the specific buttons next to the general buttons. So we have the landing leg control, searchlight controls, servo shutoff control switch, servo first and second stage, the cargo hook emergency release switch, the radio select switch, and the heads up display or HUD control switch. Next is the cyclic stick. So again, that's the fighter pilot looking stick in between the pilot's legs, and that's what provides a means of lateral and longitudinal control. So it's the helicopter tilting action that can go forward, left, right, or aft. And it does this through push rods, bell cranks, and servos connected to the swash plates and the main rotor again. So after a pilot control input on the cyclic, again the swash plate assembly tilts, and that's going to change the pitch of the rotor blades individually this time. That's the key difference between the cyclic and the collective, is that the collective, again, that changed all the rotors all together simultaneously, whereas now with the cyclic, those inputs are going to change more like one blade at a time. So it's going to be an individual blade adjustment. And these individual adjustments are going to create an uneven lift production across the main rotor disc, and that is what's going to be the source of the helicopter tilting motion. As you can see here on these pictures to the left, we have a good illustration of that whole concept. So if you look at the top left picture, this is the pilot pushing forward on the cyclic, and as a result, that motion, that force, is going to get transferred up to the swash plates, which are going to tilt the blades forward. And now, if you look at that picture, the front blades are going to be operating at a lower pitch, lower angle of attack, so producing less lift, while the blades towards the back of the helicopter are going to be now having a higher pitch, so a higher amount of lift, and that lift differential is what's going to tilt the back of the helicopter up and the nose down, and now boom, the helicopter is flying forward. So that's how the cyclic works. And the stick grip for the cyclic also has, surprise, surprise, a whole bunch of buttons on it. It's got a trim switch, a trim release switch, a go around switch, panel light kill switch, cargo release switch, a transmitter ICS switch, which is just like the push to forget button on the Cessna 172 yoke, and a stabilator slew switch. We're going to talk about the stabilator in a minute, but first we're going to go over the tail rotor. So again, the main rotors on top of the helicopter fuselage spin around. That creates the lift for the helicopter to fly, but as a byproduct of that spinning, a torque force is also created and exerted on the rest of the helicopter that's going to make the rest of the helicopter want to spin around with the rotor blades, which I'm sure would be a great time, but not really practical, and the designers and pilots don't really want that because they want to do normal helicopter things, not just spin around in a circle all the time everywhere they go. So this same concept, though, is the same as torque acting as a left turning tendency in propeller driven airplanes. Again, it's just Newton's third law. For every action, there's an equal and opposite reaction. So the clockwise spinning of the propeller exerts a rotating force in the opposite direction, causing the airplane to want to roll or turn to the left. But again, the helicopter, it makes it want to spin around in the same axis. So in order to neutralize that torque force and prevent the helicopter from just spinning around in a circle all the time, we have the tail rotor mounted on the tail boom. which is going to create thrust in a sideways direction or lift, depending on how you look at it. But it works the same as the main rotor, except it's smaller, and again, canted and tilted sideways to neutralize. This whole mission, this whole purpose is just to neutralize the torque from the main rotors. And that tail rotor is controlled via the tail rotor pedals. They provide directional control, so yaw, like left and right for the helicopter, not by a rudder pedal like on an airplane, but by varying the pitch of the tail rotor blades. And those inputs are then passed to the rotor via control rods, bell cranks, another mixing unit, control cables, and more servos to the pitch change beam. The pitch change beam is what's going to be directly varying the angle of those blades itself, and also the pedals are adjustable for pilot leg length, which is definitely helpful. Next thing is the stabulator that I mentioned earlier. So it's not an elevator because the entire surface is a control surface. It's not like an airplane or a Cessna 172 specifically, where you have a fixed horizontal stabilizer and then the movable hinge on the back, which is the elevator. The whole thing is like the movable hinge, so it's all a stabulator. And on the Blackhawk, it is a automated stabler, at least during normal operating conditions. So it's controlled automatically, and it's there because the Blackhawk has an inherent tendency to want to pitch up. The helicopter just wants to look up at the sky, so in order to avoid having the pilots having to pitch down all the time, they have this automated stabulator, which will adjust itself based on a variety of flight parameters, such as collective position, airspeed, pitch rate, and lateral acceleration inputs. So it'll move itself and adjust itself to relieve that pressure for whatever situation it's in. But it can be adjusted by the pilots in emergency situations, which we will cover later. Now, onto that mixing unit that I mentioned before. This provides control mixing functions that reduces inevitable control coupling. This could get a little bit complicated and a little bit hard to understand, but at the end of the day, it makes the aircraft easier to control and requires fewer control inputs on the part of the pilot. So the way I looked at this to understand it is that each pilot control input has primary results that are pilot intended, but also secondary results that are not necessarily intended on the part of the pilot. And the mixing unit compensates for those unintended consequences of every pilot control input. So we'll get into examples in a second, but again, it's like the pilot is manipulating the controls for a primary purpose that they're thinking in their head as they control the aircraft, but there's going to be byproducts created as a result of that. And that's where the mixing unit comes in to keep those in check. So we've got a couple different types of functions. We have collective to pitch, collective to yaw, collective to roll, and yaw to pitch. Specifically for the collective to pitch function, this compensates for the changes of rotor for the changes in rotor downwash on the stabulator caused by collective pitch changes. So again, like what I was talking about before, the primary pilot intended reaction to that control input is going to be with the increase in collective is the pilot wants the helicopter to move straight upwards. That's what the pilot is thinking. However, as a result of that, as a byproduct of that, now there's going to be more air flowing over the stabulator, which is going to change the pitch of the helicopter. So in order to compensate for that unintended consequence, the mixing unit is going to provide forward input to the main rotor as collective is increased and aft input as collective is decreased. The next type is collective to yaw, and this compensates for the changes in torque effect that are caused by changes in collective position, which makes sense if you have an increase in collective position and then an increase in lift on the main rotor blades. You're going to have more torque force exerted on the fuselage, so you're going to need to have more or increased pitch on part of the tail rotor in order to compensate and keep up for that. So it increases tail rotor pitch as collective is increased and decreases tail rotor pitch as collective is decreased. There's also a separate collective or airspeed to yaw mixing that is accomplished electronically via the stability augmentation system and F or flight path stabilization computer. Those are big words. I'm going to talk about those in a second, but I feel like I should mention it now. And then the next function is collective to roll. that compensates for the rolling moments and translating tendency caused by changes in tail rotor thrust. It provides left lateral input to the main rotor system when collective is increased, and right lateral input when collective is decreased. And the last function, finally, yaw to pitch, compensates for the changes in the vertical component of thrust of the cannon tail rotor as tail rotor pitch is changed. So the tail rotor, again, that's mounted sideways, but it's not flush. It's not totally 90 degrees sideways. It's canted on an angle, so it does still produce a small vertical component of lift. And the mixing unit compensates for that by providing aft input to the main rotor system as the tail rotor's pitch is increased, and forward input as the tail rotor pitch is decreased. Now, for pilot assistance, the automatic flight control system, AFCS, is what controls the automated stabler that we talked about before. And then in general, it enhances stability and handling qualities. Some subsystems of this are the flight path stabilization and the stability augmentation system that I mentioned before. So this is actually the topic of a whole different presentation, so I'm not going to go into it, but just at the end of the day, it enhances stability, makes the aircraft more pilot friendly. You can go check out the other presentation for details on that. And then pitch, roll, and yaw trim are all equipped on the helicopter. And again, it's got the pilot assist boost servos and collective yaw and pitch, which are going to make the pilot not have to push as hard on the controls. Makes it easier to control. Okay, now moving on to malfunctions and indications of malfunctions. The first thing that I saw in the technical manual, very first thing in the whole chapter of flight controls, was its vulnerability to radio frequency emitters. So the AFCS and/or stability control can be affected when flying near high power radio frequency or RF emitters. And those could be things like antennas or shipboard radar, and flying too close could cause uncommanded stabilator movements up to 5 degrees. It's going to mess with the automation in the stabilator and cause uncommanded movement. And the master caution light may illuminate before or during the movement. Keyword may. It might not do that. It might give you no warning, and it might just start making the stabilator have a mind of its own. So pilots need to be aware of that for sure. And then the first malfunction that we can talk about is the loss of tail rotor thrust. The indication for this malfunction is going to be a yawing motion of the nose to the right, which makes sense because the whole point of the tail rotor is to prevent that happening. Now that the tail rotor is inoperable, that helicopter is going to start to yaw as a result of that torque force. And this could be a rapid yaw when flying at low speeds. So the procedure for this is to auto-rotate and then move the engine power levers to off once landing is assured. So there's a bit to unpack here. First of all, this entire checklist, all 2 steps, are underlined, meaning they should be memory items. The pilot should be able to execute them without accessing a checklist. They can just do them right away. And next thing is the word auto-rotate. So most of us are airplane pilots. We don't have to worry about auto-rotation, but for the purpose of this presentation, it's basically like an engine out procedure for a helicopter. So in airplanes, when the engine dies, we don't just drop like a rock, we still glide. And it's sort of the same concept with an auto-rotation helicopter. So even though the main rotor blades are not going to be moving under the power of the engine, they're still going to be windmilling because of the air that's going to be passing through the blades. So the blades are still going to get spun by the air, and as a result, still generate a little bit of lift. Not enough to, actually fly or avoid the ground, but it's going to kind of dampen the fall, sort of like a glide. So that's what the auto-rotate word means. And the pilot considerations for this maneuver is that if auto-rotation is not entered immediately, the helicopter could side slip and skew the indicated airspeed reading, which is a lot like how in a Cessna 172, if you are forward slipping towards the runway, the pitot tube is no longer going to be perfectly aligned with the relative wind. So as a result of that, the ram air data is going to be off. It's going to be erroneous. And this could cause problems with the Black Hawk because if it is indeed side slipping and getting a bad airspeed reading, the automated stabilizer is going to kick in. And remember, one of those flight parameters for the governing of that stabilator position was indicated airspeed. So it's going to act on the erroneous indicated airspeed and move to a position that it thinks it's supposed to be in, but in reality, it's bad data, and now it's in an undesirable position. And again, that controls pitch up inputs, so it can make it more difficult to perform the auto rotation. So that's definitely something to consider for this maneuver. And the next scenario is a pedal bind, restriction, or drive. The indication for this could be an unnatural resistance or movement in the tail rotor pedals. Pedals are going to feel just weird, and there will be no accompanying caution legend. Caution legend, I forgot to mention before, is just like the Blackhawks version of an annunciator panel. It displays error messages and things like that. So the procedure for this would you apply firm rotor pedal force to oppose the drive, trim switch off. If normal control forces are not restored, then boost switch off. And if control forces that are normal for boost off flight are still not restored, then boost switch back on again, and tail servo switch to backup if tail rotor is not restored, and then land as soon as practicable. So we have some memory items in this checklist. It's kind of a long checklist, but basically it's checking to see if the yaw trim is what's causing that weird force in the pedals. If not, then it could be the boost switch, which could be backfiring, and normally, again, the boost switch helps the pilot not have to put as much force on the controls. In this case, it could be experiencing a hard over and a malfunction, and it could be could be hurting the pilot rather than helping the pilot. So if that's the case, it's best just to turn it off and leave it off. But if you turn it off, it still doesn't help, you can switch it back on again, and then move the tail servo switch to backup, land as soon as practicable. And then the considerations for this this checklist are that the SAS FVS computer-induced yaw trim malfunction, if that's the problem, can produce roughly 30 pounds of force at the pedals. And a jammed yaw trim actuator can produce as much as 80 pounds until relieved by clutch slippage. A malfunction in the yaw boost servo or tail rotor servo can produce higher force at the pedals, so the affected servo must be turned off. And check this out, a hard over failure of the yaw boost servo could increase control forces up to 250 pounds, 250 pounds at the pedals, which could make flying really difficult. But the good news is that as soon as you turn off the servos, those exponentially multiplied forces should be eliminated, and you can just fly the helicopter pretty much as normal. Next up is the collective boost servo hard over scenario. The indications for this would be difficulty manipulating the collective. So now the collective is going to be difficult to move if there's a boost switch malfunction. So the procedure is to turn the boost switch off and land as soon as practicable. Again, the boost switch off is a memory item. And the control forces could be up to 150 pounds in the collective. Again, same thing as before. As long as you turn it off, those forces should be eliminated. And now pitch boost servo hard over. Same thing, but now in the cyclic. I'm hoping you guys are noticing a bit of a pattern here. The procedure is turn off stability augmentation system 1 and 2 switches, and then land as soon as practicable. Again, more force needed to move the control, but should be eliminated once that switch is shut off. And now, oh, look at that, there's 2 of me, that's cool. Now boost servo off, caution legend on. Procedure for this is to turn the boost switch off and land as soon as practicable. Pilot considerations is this could indicate a jammed pilot valve in the collective or yaw boost servo, and again, control forces in the affected axis will be consistent with those present during flight with boost off once you turn it off, which is good news. Now, this is kind of a big one, flight control or main rotor system malfunction. So, yeah, kind of a big deal. The indications of this type of failure could be a varying degree of resistance, binding, feedback, or sloppiness in any of the flight controls, and it could be pretty noisy. Lots of noises or vibrations could occur as a result, and these could start out small in intensity and then increase over time, or it could just be a sudden onset of just like a hurricane of noise and vibration and shaking. And the procedure is land as soon as possible, emergency engine shutdown after landing. Those are both memory items. Easier said than done. Short checklist, deceivingly short. I'm sure in real life it would be, or in a real scenario, it would be not that easy looking. As you can see from these pictures here on the bottom, wild. Some major pilot considerations for this type of malfunction is that the main rotor system could collapse or separate from the helicopter after landing. So the air crew should exit only after the main rotor has stopped, because it would be a bad day if you survived a flight control or a main rotor system malfunction only to get slapped in the back by a rotor blade after you landed and got out, because the rotor blade didn't stop all the way. Blade strikes, skin separation, or shift or loss of balance weights or other material of the rotor blades can cause drastic changes in lift characteristics and or state of balance. I bet you didn't oh my goodness, I bet you didn't need me to tell you that. It's going to make the helicopter more difficult to fly. And main rotor flapping can result from some of those malfunctions. Reducing airspeed might help to keep the severity of any rotor vibrations to a minimum. The last malfunction is the stabilator malfunction, the auto mode failure. So again, normally the stabilator is controlled automatically, but if there's a problem with that system, the pilots will hear a beeping warning. The master caution illumination and the stabilator illumination will show up on the caution legend. And pilot considerations: if helicopter acceleration is continued or collective position is decreased with the stabilator in the trailing edge down position, the longitudinal control of the aircraft may be lost, because again, the stabilator helps with pitch control. It helps hold the nose of the helicopter down. So now if you don't have the stabilator, or if it's in a position that you don't want it to be in, you could be pitching up or down pretty intensely. So that's going to make the chopper a lot more difficult to fly. And the procedure for this is to use the cyclic mounted stabilator slew up switch to manually control and arrest the nose down pitch rate. And then auto control switch, press on once. So basically that's just reverting to manual control and then turning the auto control switch on again to try to re-engage the automatic control. If that doesn't work, then manually slew the stabilator to the 0-degree position if flying above 40 knots, or to the full down position if below 40 knots. And then land as soon as practicable. If the pilots try to move if they manually try to move the position of the stabilator and that's not happening, then stabilator position indicator check and fly at or below airspeed limits as shown on the placard, and land as soon as possible. Correction, soon as practicable. There's a difference there. Okay, that is all the content that I have for you guys. If you have any questions, please leave a comment on my discussion board post. This took a while, but I hope you're all now more informed than you were before about the UH-60 Blackhawk's primary flight control systems. And here are my references. Feel free to do some more research on your own if you thought this information was interesting. Thank you guys for watching. That was a long one, but I appreciate your time, and have a great day.